materials using scanning proof microscopy. Spin crossover materials are very interesting materials that are stable in two different magnetic phases or states, from in the low spin state that is diamagnetic to and the high spin state that is paramagnetic. These are metal ligand compounds, and they change from one state to another by different external stimuli like temperature, pressure, uh, intense external magnetic field, and light radiation. And when they transit from one state to another, they can do it following different phase transitions. They can do it doing a gradual phase transition or an abrupt phase transition, or they can present hysteresis, or they can do it in several steps. When they do the transition from one state to another, different uh, different properties of the material change, like the reflectivity. Here we show that the optical properties change from the low spin state, that is this one in pink, to the high spin state, that is this one that is transparent. But also the volume change and the mechanical properties, and we want to see that in using scanning proof microscopy. So using AFM, we wanted to study the topography change. So we used this sample that is iron pyridine, and this sample, here I show the reflection as function of the temperature, and this sample have an abrupt transition from the low spin state to an intermediate state and has a wide hysteresis. This is high temperatures. And this is an intermediate phase because here we don't have a flat surface, it still increases until the material degrades. Actually, it never gets to the high spin state. And we know this because we made Raman on the sample. And here I show the optical images of one of these crystals. Here is in the low spin state, and here is in the intermediate phase. As you can see, they have different reflectivity, clearly a difference in reflectivity. But also in the form of the crystal, it changes a little bit. And to see this more clearly, I made the topography of the crystal in the low spin state and in the high spin state. So this is only the topography, and it might not adjust well to the change in the volume, but we can see interesting things in the topography as well. For example, when we study, we found different features on each topography, and we measured these features in the low spin state and the high spin state. And when we measure in this direction, we observed a contraction from the crystal. And when we do it in this direction, we observe an expansion from the low spin state to the intermediate phase. So, and well, actually, when we see it in the optical reflectivity in the microscope, we clearly observe that this distance here decreases a little bit. No? So it agrees with what we see in the optical images. And it's a nice way to observe the spin transition. We also wanted to observe the Young modulus, and we used this sample, this iron epitresol tosylate. And here I show the fluorescence expansion of the temperature. Actually, if we do this to this sample, we add rhodamine. The rhodamine is observed in the low spin state, but is not observed in the high spin state. So we can see clearly a difference when we increase the temperature that corresponds to the spin transition. And here we observe a not so abrupt transition, and it has a very small hysteresis, almost no perceptible hysteresis. And we wanted this sample because we wanted to use this sample because when we deposit on a silicon wafer with 2 nanowires and we send current through the nanowires, this is what will happen. The material on the nanowire will increase temperature, but the material around the nanowire will not increase temperature. And we observed and verified this by the fluorescence that I do not present in this poster. But the interesting thing is that when we do the topography for different currents going through the nanowire, we observe no difference in the topography. So any change would come from a difference in the Young modulus. So here I show the map of the Young modulus in the where we send only 1 milliampere and when we send 28 milliampere. So normally the material on the wire would be in high spin state. And I made a cross section of these two maps, Young modulus maps. And what we observe is that far from the wire, we have the same Young modulus, but on the wire, we have a difference, a clear difference. So here in black, I show the Young modulus for the 1 milliampere, and in blue is Young modulus for 28 milliampere. So now we can see the difference. And the variation of the Young modulus, so the low spin state, the Young modulus of the low spin state divided by the Young modulus of the high spin state is 1.33 plus minus 0.04. So we can observe clearly a difference, and is another way to observe the transition of these materials. So we wanted to see also the change in the optical properties, and we tried with this sample, but it was impossible. We almost all the time burn the rhodamine. So it was really, really, really difficult experiment. So we needed a sample that also did not change a lot in topography. So any difference will not related to a change in the topography, but it has a clear change in the reflectivity. So we use this sample, iron eptitrazole triazole BF4, and here I show the far field reflectivity as function of the temperature. And we observe that we have a wide hystereticity above room temperature. And this would be really nice, and I will tell why a little bit later. So this is our diagram of our experimental setup. So we have the laser that is 488 nanometers that we send coupled to a fiber that is a SNOM fiber. So in the aperture of the fiber is around 200 nanometers, so it's almost half of the wavelength of the laser. And the light that is reflected on the sample is captured by this microscope objective, and is sent to a photomultiplier tube. At the same time, we can send light from the halogen lamp, and the reflected light will go to the CCD camera. So these do not intersect because we select only 450 nanometers here. So we can have at the same time both far field and near field images. So now we use the same system as before. We have a nanowire, and what we'll do is with the heater that is below the sample, we'll hit the sample to this point, so 360 Kelvin, and then we will produce a pulse through the wire, and so the wire will hit the sample that's on the wire up to here, and then we will stop the pulse, so it will cool down. So the sample on the wire would be here. So they will be taken on the same conditions in the low spin state and in the high spin state. So this is before the pulse, and this is after the pulse. So before the pulse, here we have the far field image, and here we have it after the pulse. And clearly there is it is darker here than here. So to see it clearly, we made the difference of these two images. That is this. No? So we see almost no difference far from the wire, but on the wire we see a clear difference. And we made the cross section of this, of the reflective difference between the before and after in the far field is around 6%. So now we do the same, but with snow. And what we made it for after, and here we have the difference, and we observe in the cross section the same. There is a difference only on the wire, and the difference is around 40%. So it's clearly the difference is clearly more. The difference between the low spin state and the high speed state in the reflectivity can be observed clearly or with more intensity using SNAM than far field. Another thing is that we are able to see distinguish the different particles in the SNAM that we cannot see in the far field as expected. So inclusion we can use. We can study the topography, the change in the topography, the change in the geomodulus, and the change in the SNAM using using spin crossover materials and uh, and AFM and the SNAM. But the sample is really, really, really important. No, we cannot use the same sample to study everything. We need to choose very wisely what sample we will use. So thank you all for listening. I hope you like this.